When you type a prompt into an artificial intelligence model, the response feels instantaneous and almost weightless. Text appears on a screen. Code is produced in seconds. An image takes shape without any machinery visible to the person who requested it. The experience encourages us to think of artificial intelligence as something that exists only in software, somewhere inside an invisible cloud. But the cloud has an address. Long before a model can answer, a physical chain has to be operating. Compute hardware sits inside a real building. That equipment needs electrical distribution and cooling. The facility connects to utility infrastructure. The utility depends on substations, transmission, generation, and the people coordinating the grid. Artificial intelligence becomes digital only after all of those physical layers are already working. That chain is growing more important because its electricity demand is no longer a small background detail. A Department of Energy and Lawrence Berkeley National Laboratory report estimated that data centers used about 4.4% of all U.S. electricity in 2023. The U.S. Energy Information Administration described the larger shift in January 2026. It said data centers were fueling the strongest four-year growth in U.S. electricity demand since 2000. In a separate March analysis, EIA said national electricity demand had risen steadily since 2020 after more than a decade of little change. Data centers are not the only reason demand is growing, and not every data center is built for artificial intelligence. But EIA identifies them as a driver of the change, while Berkeley Lab identifies AI servers as a major reason for recent data center load growth. So the central question is not whether artificial intelligence is software. It is. The question is, what must exist behind that software at national scale? The answer leads away from the screen and into buildings, substations, transmission corridors, power plants, and a grid that now has to prepare for a new class of large customers. To understand how artificial intelligence impacts the power grid, it helps to dismantle the abstract concept of a data center and look at what these facilities are on a mechanical level. When you look inside one of these facilities, the abstract language begins to disappear. The useful image is not a website. It is a sequence of physical systems. Compute equipment occupies rows of racks. Networks connect the equipment. Electrical systems deliver power through the building. Cooling systems remove the heat created while the equipment is operating. Security systems control access to a site built around continuous digital work. The National Renewable Energy Laboratory describes this challenge as a chip-to-grid problem. That phrase widens the frame. It asks us to follow the system from chips and computing equipment to racks, cooling, the facility, local electrical distribution, the wider transmission network, and finally the generation that supplies the grid. Each layer depends on the one around it. More computing equipment creates a larger facility load. That load must be managed inside the building and served outside it. The external connection must fit within the capacity of the local grid. The regional system, in turn, must have enough resources to serve all customers as demand changes. This is why a data center cannot be understood only as a collection of servers. Meta's own basic description calls a data center a physical building that houses technology used to process digital information. Google's educational material similarly presents data centers as engineered facilities rather than a disembodied cloud. Company material is not neutral proof of every industry-wide claim, but it is useful for seeing the machinery the word cloud tends to hide. The visible racks are only one part of the installation. Cooling, electrical equipment, access systems, and the connection beyond the property are also part of the product. For the user, an AI response may arrive in a moment. For the infrastructure behind it, there is no shortcut around the physical chain. Data centers existed long before the current wave of artificial intelligence. What changed is the pace and scale of their electricity growth. Berkeley Lab and DOE identify AI servers as a major reason that recent data center demand has accelerated. The important change is visible in the national totals. In 2014, U.S. data centers used an estimated 58 terawatt-hours of electricity. By 2023, Berkeley Lab estimated that consumption had reached 176 terawatt-hours. That is more than a change in the number of buildings. It is a change in the scale of electricity the sector requires. The report identifies AI servers as a major reason for the recent increase. It does not say that every new data center is an AI facility, or that artificial intelligence is the only source of digital demand. It says that AI hardware is now an important part of the growth occurring inside a much larger data center industry. NREL's chip-to-grid framing helps explain why that matters. The effect does not stop at the processor. A change at the chip level can affect the racks around it, the cooling and electrical systems serving those racks, the facility that contains them, and the grid connection outside the property. Growth at one end of the chain has to be accommodated by every layer that follows. Looking toward 2028, Berkeley Lab and DOE presented a range rather than a fixed outcome. Their report projected that U.S. data center electricity use could reach between 325 and 580 terawatt-hours per year. In those scenarios, data centers could account for between 6.7% and 12% of total U.S. electricity consumption. The words could and projected matter. The figures are not a promise that the highest case will occur. They describe a range grid planners may have to prepare for, while the actual path remains uncertain. Whichever path emerges, the grid has to evaluate where demand will appear and what infrastructure will be needed to serve it. To appreciate why this load expansion creates friction, it is necessary to examine the historical background of the American electrical grid. For more than a decade, U.S. electricity demand changed very little. EIA describes that period simply. After years of little change, demand began rising steadily in 2020. That reversal is significant because the power system is built and managed around the amount of electricity customers are expected to require. When the expectation changes, decisions about generation, transmission, and new connections have to change with it. The Department of Energy now describes a transmission paradigm that has shifted from stagnant demand to rapid load growth. In its February 2026 short-term energy outlook scenario, cited in a March analysis, EIA forecast national electricity load growth of 1.9% in 2026 and 2.5% in 2027. These are forecasts, not guarantees. But they show that federal energy analysts no longer see the near-term grid as a system serving a flat national load. Data centers sit inside that larger change. EIA says their electricity use is driving demand growth, and its January 2026 release said data centers were fueling the strongest four-year growth in U.S. electricity demand since 2000. Berkeley Lab's historical estimate points in the same direction. Data center use rose from 58 terawatt-hours in 2014 to 176 terawatt-hours in 2023. The new problem is not a single building or a single year. It is the need to connect many large loads while the wider demand curve is already moving upward. Grid managers regulate the interconnection of large load customers because every connection becomes part of a shared system. After years when demand offered relatively little movement, the curve has awakened. The question for utilities and regional operators is how quickly the physical grid can respond. National electricity averages provide a useful summary, but they can hide where change is happening first. The United States is served through regional systems, and the same rate of demand growth does not appear everywhere at once. A national percentage can therefore look manageable while a particular region faces a much faster local increase. Data from the Energy Information Administration highlights two regional electricity markets experiencing particularly pronounced growth in the near term. The Electric Reliability Council of Texas, known as ERCOT, and PJM Interconnection. Between 2025 and 2027, EIA expected annual electricity load growth to average about 10% in ERCOT and about 3% in PJM. Those are regional forecasts, not statements that every part of Texas or every state in PJM will experience identical pressure. They are also not claims that data centers alone produce every new unit of demand. They show where EIA expected the near-term growth rate to be especially strong. The geographic footprints are large. ERCOT covers most of Texas. PJM covers all or parts of 13 states plus Washington, D.C. In both cases, the headline growth rate applies to a system responsible for serving a broad territory, not to one isolated industrial site. This is where the national AI story becomes a regional infrastructure story. A large load connects at a specific place. Its interconnection is handled by the grid managers responsible for that region. The relevant question is not whether the country has electricity in the abstract. It is whether enough supply and delivery capacity can be made available where the customer wants to connect. ERCOT and PJM are the official examples in EIA's near-term analysis. They show that the power challenge will emerge through regional decisions about new loads, resources, and the grid between them. A large data center cannot simply be treated as an ordinary connection request. EIA notes that grid managers regulate the interconnection of both new generation and large load customers. That responsibility exists because a new customer does not operate outside the system. Once connected, its demand becomes part of the balance that the regional grid has to serve. In its National Transmission Needs Study updates, the Department of Energy noted that the core transmission planning paradigm in the United States has shifted. For years, transmission planning focused primarily on replacing aging utility assets in an environment of stagnant demand. Today, that planning framework must account for rapid load growth driven directly by large consumers. The DOE explicitly named hyperscale AI data centers as a major load growth factor that legacy transmission infrastructure must accommodate. That makes interconnection a coordination problem as much as a construction problem. The customer has a requested load and location. Grid managers have to consider that request alongside the resources and network already serving everyone else. If the existing delivery system cannot support the requested addition, capacity has to be expanded before the full load can be accommodated. The physical work can include substations, power equipment, utility corridors, and construction connecting one part of the system to another. Requirements differ by project, but the connection has to be planned and approved rather than assumed. The federal government has explicitly recognized the problem. In September 2025, the Department of Energy issued a request for information about accelerating grid capacity for rising AI and data center electricity demand. That action did not announce one solution. It acknowledged that the pace of large load growth and the pace of grid expansion have to be considered together. This is the central choke point behind the model. A completed building is not the same as delivered electrical capacity. Servers inside a property do not create the generation, transmission, or regional approval needed outside it. The digital facility reaches its intended scale only when the physical system around it is ready to serve the load. As high-voltage transmission lines route power to expanding data center corridors, a critical secondary question emerges. What energy resources are generating that electricity at the source? EIA's March 2026 analysis examined what could happen if data center demand grows faster than expected. In that high-demand case, EIA projected that most of the additional generation would come from increased use of natural gas plants. That is a modeled response, not a declaration that natural gas is the single answer to AI growth. It describes how EIA expected the existing power system to respond under a particular demand scenario. The distinction matters because this film is about a physical constraint, not a campaign for one energy source. Natural gas was the largest source of U.S. electricity generation in 2025 in the EIA analysis. That existing role helps explain why gas appears in near-term discussions of faster electricity growth. When analysts model more demand, they also have to model which available resources produce the additional electricity. This dynamic connects directly to broader domestic energy logistics. In an official press release from January 2026, the EIA pointed out that natural gas supply considerations will remain central to market balances as liquefied natural gas export capacity expands along the U.S. Gulf Coast. At the same time, domestic electricity demand is accelerating. This does not mean one side must give way to the other. It means the AI power story intersects with a larger energy system in which generators, fuel supply, exports, transmission, and new customers are connected. At the end of the chain, artificial intelligence still requires generated electricity. EIA's high-demand case gives one official view of where much of that additional generation could come from. It is a forecast to plan around, not a permanent verdict on the future power mix. Discussions surrounding data centers and the power grid often lean toward extreme rhetoric, predicting immediate, catastrophic blackouts across entire states. The reality identified by professional grid reliability coordinators is more nuanced, focusing on operating margins and resource adequacy. The North American Electric Reliability Corporation evaluates long-term reliability conditions across North America. In its 2025 Long-Term Reliability Assessment Summary, NERC identified rising resource adequacy risk over the coming decade. In practical terms, the assessment asks whether the power system is keeping enough dependable capability in step with the demand it expects to serve. NERC's summary said new data centers for AI and the wider digital economy account for most of the projected increase in summer peak demand in its assessment. That finding does not mean a blackout has been scheduled or that every region faces the same level of risk. It means planners cannot evaluate future reliability while treating these new loads as a minor detail. The size and timing of demand have become part of the adequacy calculation. EIA describes the mechanism conditionally. If demand grows faster than available supply, stress can appear as wholesale electricity price spikes or, under more severe conditions, rolling blackouts. This is not a forecast that either outcome must occur. It is an explanation of what can happen when supply and demand move out of step. The language of risk is important. NERC identifies a direction requiring attention. EIA describes a conditional mechanism if demand outruns supply. Neither says failure is inevitable. Both point to the same planning challenge. Growth has to be matched by resources and delivery capacity. Reliability is therefore less about one dramatic prediction than about preserving room to operate. The margin can be strengthened by what is added, when it becomes available, and how quickly the grid can connect it. That is why the debate reaches beyond the walls of the data center. Once grid capacity becomes a recognized constraint, the natural response is to search for ways to move faster. The Department of Energy's 2025 request for information reflects that search at the federal level. It asked how grid capacity could be accelerated for rising AI and data center electricity demand. The useful point is not to nominate one preferred workaround. The useful point is that every credible response still has to operate somewhere inside the same physical chain. NREL's chip-to-grid framework begins at the computing hardware, but it does not end there. It follows the system through racks, cooling, facilities and campuses, electrical distribution, transmission, and generation. Improving one layer can change the pressure on another. It cannot make the other layers disappear. A more efficient computing system still operates inside a facility. A facility still needs cooling and electrical distribution. A faster connection process still has to result in a connection the wider grid can serve. Additional generation still has to reach the customer. New transmission still has to connect the places where electricity is produced and consumed. This is why construction footage from a microgrid can illustrate the broader point without being presented as footage of a commercial AI facility. It shows that an alternative electrical arrangement is also an infrastructure project. Equipment has to be installed. Conductors have to be placed. Systems have to be connected and coordinated. DOE has identified the need to accelerate capacity, but the locked record does not establish one universal answer. Regions begin with different resources, networks, and forecasts. The workaround, in other words, is never purely virtual. It may change where the work occurs or how the pieces are coordinated. It does not remove the need for chips, cooling, facilities, grid equipment, transmission, and generation to function as one connected system. The public discussion surrounding artificial intelligence focuses overwhelmingly on digital breakthroughs, parameter counts, algorithmic efficiency, chip architectures, software capabilities, and market valuations. Yet behind every advance in machine intelligence lies a basic infrastructure reality. Before a model can produce text, analyze information, or generate code, a physical chain must be available. Computing equipment, cooling, a facility, electrical distribution, transmission, generation, and the grid systems connecting those layers. National electricity demand is rising after more than a decade of little change, and EIA identifies data centers as a driver of that growth. DOE says the transmission paradigm has shifted toward rapid load growth and specifically names hyperscale AI data centers as a factor the legacy grid must accommodate. NERC says those new data centers account for most of the projected summer peak demand increase in its 2025 assessment. Those statements do not predict collapse. They identify work. New large loads have to be evaluated. Supply and delivery capacity have to keep pace. The regions feeling the strongest near-term growth have to make those decisions while forecasts are still changing. The future scale of artificial intelligence will not be decided only inside software laboratories or chip plants. It will also be shaped by the speed at which the physical power system can prepare for and connect the demand behind it. That preparation will not happen in one place or through one decision. It will happen through regional interconnections, transmission planning, resource choices, and construction carried out before the next wave of computing can be fully powered. Artificial intelligence feels digital, weightless, and immediate, but it becomes digital only after the physical grid is already working.